Reinforcement learning is somewhat special in that it receives some teaching signal, but not as much as in supervised learning. So it sits somewhere between supervised and unsupervised learning. The teaching signal that it gets is either whether it has done something good or bad. So it's a scalar teaching signal. But what's so special about reinforcement learning is that you have an agent that has to make decisions, right? Either it can go left or it can go right, for instance. Once it has done that, it gets either reward or punishment, depending on whether it was good or bad. And typically that's just called reward, can be positive reward or negative reward. So I recommend to pause here for a moment and read this very nice short description of the essence of reinforcement learning. However, I will go straight to the more formal description and use this didactic example for that. So in reinforcement learning we have states, and states are these little boxes, and the agent can be in that state. So X is the agent, and the blue square here is the state in which the agent currently is. The agent can take actions. In this case it can, for example, go down, it could also go left, or could go up. If it's in the middle somewhere, it has 4 directions where it can go. In this case, in this particular scenario, that's just one example, the agent gets a negative reward of -1 for each step that it takes, but it does not have the option not to move unless it is in one of these 2 red squares, which are the absorbing states. So once it arrives in this state, it is allowed not to do any step anymore. So, and since it gets a reward of -1 for each step that it takes, of course it should move as quickly as possible into one of these 2 absorbing states and then just rest there. So it can thereby minimize its negative reward. The states have a description. In this case it's the coordinate of the box, and they have a value, -4 or -3 or whatever. These values are unknown to the agent, so the agent has to learn these values, and it has to learn a so-called policy. A policy sort of is a strategy how to move in that environment. And these two are closely related, as we will see in a moment. Ideally, the value of the states corresponds to the expected reward given an optimal policy. Right? So each time the agent moves from one state to another, right? Each time my little agent here moves from one side to the other, it gets a reward, and in this case the reward is R of t is -1 for each step that the agent takes. And that is this reward. And the expected reward is simply the sum over all the rewards that the agent gathers from now, which is t0, to the infinite future. And that, of course, depends on the state in which the agent currently is. So this is S of t0, which is referred to here as S0. So right now the agent is in state S0, and then it takes a series of actions, and for each action it receives a reward. And if you sum all that up, that would be the reward that it gets. And if it's sort of a prediction about the future, that would be the expected reward. So in the example above, if we assume that the agent has this policy. So for each state, there's an arrow that leads into another state, right? Except for the absorbing states. And that is a policy, right? So the agent can behave according to these arrows. And if it does, these are the true values of the states, i.e. these are the expectation values for the reward. For example, if the agent is in this state, then according to this policy it would first move to the right and then down. And if you do that, we get a reward of -1 for this step, -1 for this step, etc. So we add 1, 2, 3, 4, 5 steps which add up to a expected reward of -5. That's why this state here has the value of -5. So this is a true value of all these states, right? I mean, these states are nearer to this absorbing state. So these are the true values of the states given this policy. Now, but obviously, I mean, we already see that this is not an optimal policy. It would be much better to move directly to the left if the agent starts in this state. These are the true values given this policy. But these values are not known to the agent, so the agent has to learn that. So how does that work? So let's look sort of at a maybe a lower right corner. So let's assume, and this is the absorbing state, right? Okay. So the agent, I mean, has a map or a function that expresses the value of the different states. And initially, of course, there are wrong values in this. So let's say there's 3 here, there's 4 here, there's -1 here, 5, 1, 2, -3. Yeah. And okay, and the agent, I mean, let's tell the agent that this has the value 0, because once it is there, it doesn't have to move anymore, and then it doesn't get any punishment anymore. So let's assume the agent, we put the agent somewhere, right? We put it here. Then the question is, okay, what should the agent do? The agent can actually not plan ahead, but it can see the values of the states directly around it. Right, so let's put it -3 here and a -4, so that there's very little incentive to go there, and -5 here. So let's consider this situation and sort of with this policy, how the values that are initialized to these wrong values, how they can be corrected and learned to these correct values. And we follow strictly this policy. We will consider how to optimize the policy in a moment. But right now we fix this policy and we just try to learn the value function. And we do that by placing the agent randomly in different locations, in different states of this environment, and then see what it can do in order to adapt, learn the values to correct values. Okay, so let's put the agent in this state, and then it moves by the policy, it moves to the right. Yeah? So now it sees here it has a value of 5, and it sees it has a value of -1 here, and it feels that it gets a punishment of -1 or a reward of -1 on the way to this state. Now it's quite obvious that the value of this state cannot be 5 if you move into a state with a value of -1 and you receive a punishment of -1 on the way. Yeah? So this value needs to be corrected to a value of -2. -2 is the expectation value or expected reward in this state plus a reward on the way to this state. Yeah? So what we do, we correct this 5 to a -2. Yeah? Now the agent is in this state. It will move according to this policy, right? It will move down. It sees an expected reward of 4 and receives a reward of -1 on the way. And that means -1 is not a correct value, right? It should be 3. So we correct this to 3 because that's 4 minus 1, right? If the expected reward is 4 in this state, then it is 3 in this state if it moves down. Okay, finally it moves down to this absorbing state, and with the same argument, the value 4 is incorrect. It should be -1. Yeah? And now we see at least this value is correct, right? That's the correct value, but the others are still wrong. So now we place the agent again into one of the random states. Let's say we put it here. Then same argument, the value should not be 1. It should be 2, right? 3 minus 1. Then it moves to the right, so it should not be 3. It should be -2. Right? And then we go down, and that's fine. The value is correct. And by repeating many of these processes, so we place it here, let's say this gets corrected to -3, right? Then we go from here to there, this gets corrected to -1. Then we start here again, this gets corrected to 2. Then from here to there, this gets corrected to -2. This is correct, etc. Then we place it here again, let's say, then this gets corrected to -3, and so on. Yeah? If we're here, gets corrected to -3. If we're here, and so on. Right? So by going through these different states and always updating the state where it comes from by the value of state where it goes into, plus the reward that it receives on the way, the values become more and more correct. Yeah, until it converges to this situation. So this is how the correct value function can be learned if you have a fixed policy. And that's written in an equation here. So the value in the next time step of state S equals the value of the state that it goes into, and that's given here by this capital S function. So capital S is the state where you get into if you're currently in state S and you take an action A that's possible in state S. Yeah. So a state and a particular action brings you into a new state. Yeah. For example, if you're in this state and you take the action going to the right, then you're in this state. So this is the capital S state and this is the lowercase s state. Yeah. And you take that value, so you take this value and you add the reward that you receive if you're in state S and you take the action AS. Right? So this formalizes exactly what I've just shown. Okay, so now we know how to get the correct value function given a policy. However, we have already remarked that this is not an optimal policy, right? From this state, it would be much better to move to the left rather than to the right. So how can the agent learn an optimal policy given a value function? Well, there's not much learning, actually. It should simply look into the neighboring states and then move towards that state that gives a maximum reward. at least in this case where the reward on the way into that state would be equal in all cases. Yeah. So if the agent knows what the reward is, it gets if it does a step into another state and it sees the value in that state, it can figure out what's sort of the optimal direction to go. And in that sense, it would be optimal to go from here to there rather than from here to there. Yeah. And this is expressed by this equation. So the action that the agent takes in state S should be the one that gives the maximum expected reward. And the maximal expected reward, so this is the maximum operation here, over the different actions that are possible to take, right? A dash are the different options that the agent has. And this expected reward is a combination of the value of the state where the agent ends up in after having done this action and the reward that it receives on the way into this state. And that's the sum, and then the agent simply figures out what's the optimal action to take based on this. So there's no real learning here involved. That is something that can be done right away. So here we see what happens if we iterate these two processes. So we iterate deciding on a policy, then learning the correct value function, then based on that decide on the optimal policy, because we have seen it is not optimal to go from this state to that state. It would be rather optimal to go to the left state. So that would be the optimal policy given this value function. Then based on this policy, the system can learn a new value function, because now it realizes that going from this state to that state makes this expected reward -1 rather than -5. And now it turns out that going from this state to that state is better than going to the right. So we adapt the policy again, and then based on that we can learn the true value function. And this now is the true value function, and this is actually an optimal policy. I mean, if the agent is in this state, it could also go to the left. So it's not a unique optimal policy, but it is one of the optimal policies. Now it's not very efficient to first converge completely on the true value function and only then decide on a new policy. It's better to do both simultaneously, actually. And this can be done by combining the two equations that we had above. So the action that we take is always the optimal action in that current situation, right? Given the value function that we currently have, we take the optimal action. This is how the agent decides where to go, and then we use the equation from above to update the value function. So this would be the most primitive, simplest form of reinforcement learning. So that is known as temporal difference learning, although there are more refined versions of that, and there are a lot of ways to improve on that. In particular, there are also ways to deal with uncertainty. Right now we have argued we have a deterministic system, deterministic environment, but you have to use some other strategies if you have a probabilistic environment. But this is sort of the most basic version of reinforcement learning and gives you sort of a feeling for what the principles are. Standard reinforcement learning, or temporal difference learning, as we have learned it in the first section, is rather inefficient. One problem is the very slow update of the states. So if we consider a very simple variant of the system that we have considered so far, where we have these states, and we have one absorbing state. So the box in the state in the very right is the absorbing state. Let's assume the boxes are all initialized with some values. Okay, so let's put it in. Oops. 3, 4, 1, 1, minus 3, minus 5, 2, 5, minus 3, minus 1, 3. And we know this has a value of 0, right? Now, and we place the agent in some of these states, and then it has a choice of going left or right. Yeah. So if this one is about for some time, and then in the end moves from this state, with a 3 in there, to the last state, then it learns that the value here should actually be -1. Yeah. But it has learned nothing about the other states. If then it wanders about again and again, then it eventually updates this state to -2 correctly. It leaves this at -1. Yeah. So it has learned the value of a second state, right? So it needs to run through this over and over again until the true value sort of gradually propagates back into through the states. Now, one can improve on this by not only updating the value of the state which I just leave, but also the previous states. So let's assume we put the agent here in this box, and it moves right straight to the right. Yeah. Then it learns from here to there that the value 2 is wrong. It should be 4. Yeah. And now at that moment we don't update any other values because we have just started. Yeah. If then the agent moves from here to there, it learns that the value here should be -4 rather than 5. No. Now the value here has changed from 5 to -4. So it has changed by 9. Yeah. And now that can help us to update also the value of the previous state to correct that, because that used to be the correct value for the 5 that was in here. But now it should be reduced by 9 like this state. So it is corrected along with this one. So we put it was a 4 minus 9 would be -5. Yeah. So now the system has learned in one go the two states. Now that would in principle work in such a one-dimensional thing. Yeah. So you could actually start here on this side and let it run once, and then it would learn all the different values in one go. Yeah. There are problems if you consider a two-dimensional environment and for example you imagine for some reason the agent is running in a circle, right? Then if you would really do this strict updating, then it would update this point twice and then would get a wrong value, right? So it's maybe not a good not a good strategy to update it by strictly the same amount by which you update the current state, So it might not be a good idea to update the values of the previous states by as much as you update the value of the current state. So there should be maybe a decay, so the past should be corrected less in order to avoid these kinds of problems. And this is what is being done in what's called TD lambda learning. So what you do here is, so this is a standard learning rule that we had above. So we update the value of the current state as of t. We update it, so we look at the value of t plus 1 by the value that the next state has, that is vt of st plus 1, the value of the future state plus the reward. And now what is added to this is that you also update the values of the states that have been previously visited. So st minus t dash. So these, because of the minus t, these are the states that have been previously visited. And you update these, right, so they're going from vt to vt plus 1 by the difference of the value of the current state. This is the update of the current state, and this is the value, the current value of previous states, right? So you simply correct the previous states by the adaptation of the current state. If this prefactor would be 1, then we had the situation that I've just described, that would allow this one here to update all states from left to right. But typically one chooses a value somewhere between 0 and 1 to avoid these problems, and one takes the exponent t dash. So the previous, the value of the previous state is updated most, and then as you go into the past, they will be updated less and less. If you have a system, if you have an environment with no absorbing state, so the agent will never finish the job, then you might run into trouble because the agent moves all the time. That reward will add up to infinity, right? If you have, let's say, a reward of -1 for each step that it takes, it will just go to minus infinity. Or if you're more positive, right, you give the agent a reward of +1 for each successful step that it does, then the expected reward will end up plus infinity. So this would, for instance, be the case if you have a situation like pole balancing, right? So imagine you have a little cart here that can move left and right, and you have a pole that's being balanced, right? So in this case, right now, and what the cart can do, it can move left and right, and it's limited, right? It's limited here in the left and right, so it has to balance the pole within that 1 meter or whatever. Right now it should probably move to the right so that it balances the pole. The state in this situation might be described by an angle, this angle, and maybe the position of the cart. Would be two-dimensional state space. Maybe also velocity that can vary. Now, the job for this agent is to balance this pole. And so you would give it positive reward for every second that it manages to balance the pole. And if you would just add that up, and if the agent is successful, then this reward would add up to infinity. So you have an ill-posed problem. What you can do about this is you can discount the reward. Right? So the expected reward would not be just the sum over the reward that it accumulates, but as you go further into the future, the reward is discounted by a gamma factor. Yeah, so t goes to infinity, so the exponent becomes larger and larger. t0 is the current time step, and you can imagine that if this is a factor between 0 and 1, then with this exponent, the reward in the very future would not count anymore, basically. Right? So this is a way to well define expected reward if you have an environment with no absorbing states. Now, in order to reflect this expected reward in the value function, you need to discount, you need the discount factor there as well. So the update rule that we had above would be corrected by just adding this gamma factor here. So the new value of state S is the reward that you get by taking action A in this state S, plus the value in the future state, so S of S and A is the state where the agent goes into, but discounted by gamma. And if you do that, you end up exactly with this equation of expected reward, because of course this value contains also information about the value one step ahead, but that would get two gammas, right? Gamma times gamma, because it's 2 steps ahead. And that in the end leads to this gamma exponent expression that you have up here. I've mentioned already that it's also possible to deal with non-deterministic transitions, but you have to adapt the equations a bit for that. Right? So let's assume we have transition probabilities. So if the system is in state S and takes action A, then it will not deterministically go into a new state S dash, but there will be probabilities that are expressed here as P of S dash given S and A. Now if you had these probabilities, you could update the value of the state by adding the reward that you get for taking that action in that state and a weighted average over the values of the state you might end up in, or you might transition to. And the probabilities are these P of S dash given S and A. Problem is these probabilities are not known, so they have to be learned along with the values. So one possibility would be to really just count the numbers you end up in a particular state if you are to count how often you end up in state S dash if you're in state S and take action A. So you can assume these probabilities. However, that's expensive in terms of memory capacity at least. So what you actually do is you learn the so-called Q function that's expressed down here. The Q function assigns a value to a particular state action combination. Right? So the values are now not assigned to a state, but to a state action pair. If you have that, it's easy to calculate the value of a state by simply taking the maximum over Q over all actions. Right? Obviously, the agent would take the action that promises the highest Q value. Yeah? And that's described down here. So the action taken would be the the one that gives the highest Q value if you run over all A dash possible actions. Now how do we update Q? Now if we had a deterministic situation, we would update our Q for state S and action A by the reward of S and A and the value of the state we transition to. Right? S dash would be the deterministically determined new state given we are in state S and take action A. However, in the probabilistic case, where we have non-deterministic transitions, this S dash is not clearly determined, right? Sometimes maybe with 20% it would be, you would go left, and with 50% you would go down, and with 30% you would go right or something. So you would need to average over the different states. I mean, if we had the probabilities up there, we could actually do a similar trick like here, yeah, but we don't have that. So what we simply do is we use a so-called leaky integrator. So we don't replace the old value, which is Qt of S and A, completely by this new value, but we simply replace a fraction of it by the new value, which is this one here. And alpha is the fraction that determines how much we replace by the new value, and we keep partly the old value. So let me illustrate that. So let this be the Q value, and the initial Q value should be 1. Yeah. And now let's not worry about the different states, etc. Let's just say there come sort of two different values, namely 1 and 0, and they come with 50% chance. So let's just look what happens with Q if we update it according to such a rule where we just assume the value that we just get, or if we update it to according this rule where we just replace 20% of the Q value by the incoming value and leave 80% at the old value. So let's first do the deterministic thing. So we get the values 0 and 1 with 50% probability. And we start with a value of 1. Yeah. Now let's assume the next value is also 1. I mean, then obviously we take that value. The next value would be 0, so we would just take the 0 value. Then maybe a 0 again, and then a 1 again, a 0, a 1, etc. Yeah. So in that case, so if we use this version here, the value would just jump back and forth between the two possibilities. And the two possibilities correspond to the two S dash possible values that we here assume. Now if we use this rule down here, it's different. So we add 1 and we get another 1. So that would be, of course, again a 1. So we have the same value. Do a little cross here. Now if the next value is a 0 and we replace 80% of this value, we don't set the value exactly to 0, but we just replace 20% of that by 0, then we get an 0.8. Yeah. The next value is a 0 again, so we go down another 20%. The next value is a 1, so we go up 20% on the way from this value to this value, so we have a value here, let's say. Then we go down again a little bit. We go up a little bit and go up a little bit even further. Right? And what happens is that depending on whether you have zeros or 1, it sort of zigzags back and forth, always just moving 20%. And it will average in the end around this 0.5, which is a theoretical prediction. Yeah? So that's what you get. That's what you can achieve if you use this leaky integrator, or leaky summation, as it would be probably better called. If alpha is large, you jump back and forth more. If alpha is small, you jump back and forth less, but you also converge slower to the true value. Yeah, so this is a parameter you have to think about. Okay, I said that using this Q value is more efficient than estimating these probabilities, because if you have 1000 states and 10 actions in each state, then this would be 10 million, 1000 times 1000 times 10 million probabilities you have to estimate. While Q only has the variables S and A, so that would be 10,000 rather than 10 million, and that's a big difference. Right? So therefore this is more efficient than estimating these P's, these probabilities, and then going from there. Now, if you have a probabilistic system, so if the transitions are not deterministic, you have a trade-off between exploration and exploitation. Yeah? Exploration means you try different things, right? So if you're in a state and you have 3 possible actions, you try all of them out in order to figure out, okay, what will be the expected reward if you take that action. Exploitation means if you've learned already something about the payoffs of the actions in that state, then you should take the action that gives you that promises the largest payoff, right? So that would be exploiting what you have learned already. And this is a trade-off because if you too quickly go into the exploitation mode, so you might not have learned the expected reward, so your Q values might just not be right. Yeah? And I want to illustrate this with this example here. So let's assume the agent always starts in state S1, and then it can take the action A1 or 0. And from then on it just runs through this whole thing, so there's just one action to take. Yeah? So if it takes action 1, it gets a reward of 1 here, it transitions to S4, it gets another reward of 1, and transitions to S5. Right? So quite obviously the expected reward along this line, along this path, would be 2. Huh? So Q of S1 and A equals 1 would be 2. Now let's assume it has, and this is something that the agent can figure out with, going through there once, right? But let's assume it has sort of tried 4 times the 2 actions A equals 0 and A equals 1, and with equal probability. So it has chosen this twice and this twice. Now if it chooses this twice and it once goes over the top path here, and once it goes through, takes this lower path here, right? Then the system, if you just average over this and don't worry about the details of this leaky summation, then we would get a Q of S1 and A equals 0 of, well, if you go this way, we have a reward of -2. If we go this way, we have a reward of +4. So the reward on average, averaging just over these two trials, would be 1. Because the -3 and the +3 cancel out. However, if we look at this one here, we see that the probability of getting a -2 is 0.1, while the probability of going down here is 0.9. Yeah? So this would be the estimated Q value after the two trials, which happen to be one up here and one down here, but the true Q value would be, so this is estimated, and this would be true Q of S1 and A equals 0. So that would be 0.1 times -2 plus 0.9 times 4. Yeah. And that would be, I mean, if this were a 1, then this would be 4, but we have to reduce this by 10%, so that would be 3.6, and then we reduce it by another 0.2, so that would be 3.4. So here we see that by just averaging over the two trials that we had, we get a too low value by chance. And if we would now decide to always choose A equals 1, because there we get reliably a value of 2, which is greater than this 1, then we would just have not done the right thing, right? Because the true probability, or the true expected reward here, for A equals 0 would be 3.4. Yeah? So you have to try often enough the different options before you decide on one particular strategy or policy. If you're in a non-deterministic system. Yeah? Reinforcement learning has successfully been used also for game playing, for training a game playing agent. Now in that case, you have two players. So how do you deal with the situation that you have two players and you want to train reinforcement learning? Well, that's relatively simple and illustrated in this picture. You simply treat the other agent as part of the environment, and then it becomes a probabilistic environment because the other agent might change its policy on the way. But otherwise it goes through straightforward, right? So let's assume we have such an environment, and we have a sort of this is the state in which the game is right now, and we have a player A and a player B that alternate in their decision, right? So in this case, player B starts first, and the goal of, now let me check. Yeah, so the goal of player A is to reach this absorbing state, while the goal of player B is to reach this absorbing state. Right? So let's assume B starts, it moves down. Then it's the turn of player A, it moves left. Then it's the turn of player B, it turns down again. Then it's the turn of player A, it moves left again, etc. So that way you have this path. Now, if you only look at the role of player A, for player A it looks like it takes a decision. Now it is here, takes a decision, namely left, and it ends up down. So this is a probabilistic decision, probabilistic transition to this down field, to the lower left field, due to the action left. Then it takes the action left again, and it ends up here. But it could also have ended up here if player B had decided to move to the left. Right? So the other player adds some randomness to the transitions here for player A. And in this case, player A has won, right? Because player B has dumb moves. Okay, so the last extension I want to talk about is an extension for large state spaces. In particular in games, because you have many positions like backgammon, for example. That's a game that has been played by successfully trained with reinforcement learning. These games have a huge state space, right? So there are many different ways the stones can be on the board. Much too large for the standard discrete reinforcement learning to work that we have seen so far. So what you can do in these cases, you can approximate the value function by neural network, let's say. So you need some function approximator that works in the state space but has much fewer parameters than you would need to represent all the values of the different states. So these were a few simple extensions to address some problems that you might run into in reinforcement learning. There's of course much more to it, but I will stop here.